Hello, welcome to S Mathematics. Now in this video we are going to see problems from subgroups 4. Why we are doing number of problems means in order to make you understand the concept clearly. Now what do you mean by subgroup? Subgroup is nothing but a subset plus group. That means in a group if you take a subset, it is called as a complex. Non-empty subset of a group is called as complex. Any non-empty complex is becoming a group with respect to the operation of that group, then it is called a subgroup. This is the definition of the subgroup. Now see the problems. Now the first one is, if G is a group of non-zero real numbers. What is G? G is a group of non-zero real numbers with respect to multiplication. What is the operator? Operator is ordinary multiplication. Prove that the H is equal to the set of all x belongs to G. X is equal to 1 or x is irrational number. Real numbers means it contains rational and irrational number. If x is equal to 1 or x is equal to irrational, then x will be in H. What is H? H is a non-empty subset of the set of real numbers. But that set of real numbers is forming a group with respect to addition. Now what you have to prove is, this H is not a subgroup. It is subset, but it is not a group. That we have to prove. Okay. Now similarly, in the second problem, if k is equal to x belongs to G, x greater than or equal to 1 is not a subgroup. Here you have to show that H and K are not subgroups. With respect to which operation you are thinking? The operation of G, the operation of H will be the operation of H. Okay. Now see here. Given that H is a group of non-zero real numbers under multiplication. Now H is equal to x and x is equal to 1 or x is irrational. Suppose x is irrational. Take any irrational numbers. Therefore root 2 belongs to H. But root 2 into root 2 is equal to 2. 2 is not irrational or 2 is not equal to 1. Therefore this 2 does not belongs to H. Therefore you will say that closure property is not satisfying with respect to multiplication in the given set H, where x belongs to G, x is equal to 1 or x is irrational. H is defined in such a way. How H is defined? H is the set of all x belongs to G. What is G? G is set of real numbers which is forming a group with respect to multiplication. Non-zero real numbers. That means you are eliminating 0 or minus 0, you are saying. See girls, usually when you take the operation as the multiplication, in that set 0 won't be there. That you have to remember. Okay. Now root 2 belongs to H, but this does not belongs to H. Closure property itself is not satisfying. Therefore it is not a group. Because it is not a group means itself is not any non-empty subset which is not becoming group with itself with respect to the operation of the main group, then it is not a subgroup. Okay. Similarly, x belongs to G, x greater than or equal to 1. Let 2 belongs to K, but 2 inverse is equal to 1 by 2, but that does not belongs to K because x belongs to G, x should be greater than or equal to 1. But x being half, here 2 inverse being half, it will be less than 1. Therefore, K is not a subgroup of G. Now is it clear? R is the R minus 0 is a group with respect to multiplication. For that you have defined two sets H and K. Then you have to verify whether they are the subgroups or not. I think it is clear they are not subgroups. Now see the next problem. If G is a group, the set N of A is defined as x belongs to G such that Ax is equal to XA for A belongs to G. Then prove that NA is a subgroup of G. NA is subgroup of G means if you take x1 comma x2 belongs to NA, and I am saying that if x1 comma x2 inverse belongs to N of A will be the subgroup. From where you got it? From the necessary and sufficient condition. If H is a non-empty subset of G, H is a non-empty subset of G, by necessary and sufficient condition for a non-empty subset to be a subgroup, for every A comma B belongs to H, AB inverse belongs to H, then H will be the subgroup. That property we are going to use here. Now what is given to you? Given that G is a group. And how N of A is defined? X belongs to G. Ax is equal to XA. Where is A? A is also in G. So Ax is equal to XA for A belongs to G. Since G is a group, E will be there. So A belongs to G. AE is equal to EA. A belongs to G for any A in G. Okay. Now take x1 comma x2 belongs to N of A. Now Ax1 is equal to this you have taken. If you take A belongs to G, that A will be in N of A satisfying this condition. Okay. Now Ax1 is equal to x1A and Ax2 is equal to x2A. x1 comma x2 belongs to N of A. What is the condition in N of A? Ax should be equal to XA. Therefore, Ax1 is equal to x1A, Ax2 is equal to x2A. Why? Because x1 and x2 belongs to N of A. N of A is defined in such a way. Therefore, now since consider Ax2 is equal to x2A, multiply on both sides with x2 inverse. So x2 inverse Ax2 x2 inverse, x2 inverse x2A x2 inverse. That is x2 inverse A is equal to Ax2 inverse. Therefore, x2 inverse belongs to N of A. Now what you got? x2 inverse belongs to N of A. Okay, that means Ax2 inverse is equal to x2 inverse A by the property of N of A. Is it or not? Now you got it. Okay. Now see next. They consider A of x2, x1, x2 inverse. What is your idea? Your idea is you want to show that x1, x2 inverse belongs to N of A. In order to say that, what you have to prove? A x1, x2 inverse should be equal to x1, x2 inverse A. This you have to prove. For that, you have consider A x1, x2 inverse. And what are A x1, x2 inverse? They are all the elements of G. So you can write it as Ax1 into x2 inverse. Ax1, it is commutative group, can be written as x1A, or you can take from the group x1 and x2 in NA. NA is Ax is equal to XA. So Ax1 is equal to x1A. From there you can take. So x1 comma Ax2 inverse. Now x1 comma x2 inverse A you can write. This inverse this is x2 inverse A. Therefore, x1 x2 inverse A, x1 x2 inverse A. This is the condition you have to prove. Therefore, x1 x2 inverse belongs to N of A. You have taken x1 and x2 in N of A. You are able to show that x1 x2 inverse belongs to N of A. Therefore, N of A is a subgroup of G. Now, is it clear? Is it clear? Okay. Now, see the next problem. This is one of the important problem. You have to practice it. Let A be any element of a group G. Then the set H is equal to A power N. For N belongs to Z is a subgroup of G. If K is a subgroup of G and A belongs to K, then prove that H is the subset of K. See here. What is the statement? See girls, in the examination or while doing the problem, first you have to read twice or thrice the given problem and confirm what is given, what you have to prove. Get clear idea. Then only you can do the problem. Okay. Now what is given to you here? A be any element of a group G. The set H is equal to A power n, where n belongs to G, is a subgroup of G. This we have proved in previous videos. Now what you have to prove? K is a subgroup of G and A belongs to K, then H will be the subset of K. That you have to prove. See here. A be any element of G. Okay. H is equal to the set of all A power n, n belongs to Z. Now we prove that H is a subgroup of G. In order to prove that H is a subgroup of G, you can take two elements from H, A comma B from H. A B inverse belongs to H. By necessary and sufficient condition, your problem will be over. See here. 1 belongs to Z. Okay. Therefore, A power n is equal to A belongs to H. H is a non-empty subset of G. Okay. Now, see here. Let A, because it is non-empty, you can take two elements. A power R into A power S belongs to H. So, R comma S belongs to Z. Now, XY is equal to A power R into A power S. A power R plus H belongs to H. R is where you have taken R in Z. So, minus R will also be in Z because Z plus is a group. Inverse will exist, additive inverse. R inverse is minus R. So, A power R minus whole power n is equal to A power minus R belongs to H. That means, if you take A power R into A power S, that is A power R whole power minus 1 belongs to H. That is here, what is the necessary and sufficient condition you have used? According to the first necessary and sufficient condition, if H is non-empty subset of G, H will be a subgroup if in H closure property satisfies and every element of H is possessing its inverse, then H will be a subgroup. You said, you proved that theorem. According to that here, XY, A power R into A power R plus S belongs to H because R plus S is an integer, sum of two integers is an integer. R belongs to Z, Z is an additive group, minus R belongs to Z, therefore A power R whole power minus 1 belongs to H. Therefore, H is a subgroup of G. Let K be any subgroup of G and A belongs to K. A belongs to K, K is a subgroup of G, therefore A power n belongs to K. Because K is a subgroup, closure satisfies. A into A belongs to G, A square into A belongs to G, A cube into A belongs to G, like that A power n belongs to K. Therefore, H is a subset of K. These are all only the problems here. If you solve these problems systematically by knowing the logic, your logical thinking will be improved. Okay. Now, see the next one. Show that the set of all elements of an abelian group G, which satisfies A square is equal to E, form a subgroup of G. In groups problems, you have shown that if all the elements in a group are inverses to each, are having itself as inverse, then it will form an abelian group that you have seen. Now, what is this? The set of all elements of an abelian group G, which satisfy A square is equal to E, forms a subgroup. Now, take G is abelian group. Abelian group means for every A comma B, A dot B is equal to B dot A. This is the problem, abelian group. Now let H is equal to the set of all A belongs to G such that A square is equal to E. Now you have to prove H is a subgroup of G. Now here also we are using necessary and sufficient condition. For any A comma B belongs to H, AB inverse belongs to H, then H will be the subgroup of G. Now see here, G is a group, E belongs to G, E square is equal to E. Therefore E belongs to H. Therefore H is non-empty. Since H is non-empty, you can take two elements from H. Let A comma B belongs to H. Then A square is equal to E, B square is equal to E according to the definition of the set H. So A square is equal to E, B square is equal to E means A is equal to A inverse, B is equal to B inverse. Now consider AB inverse whole square. If that is equal to E, AB inverse belongs to H. For that purpose you are considering AB inverse whole square. AB inverse whole square is equal to AB inverse into AB inverse. AB inverse can be written as A into B inverse, B inverse A into B inverse. You can arrange the terms like this because they are all the elements of G. G is a group. So A into B inverse, AA into B inverse, B inverse. This is A square into B inverse whole square. But what is A square? A square is equal to E and B inverse whole square is equal to E inverse. Therefore, E dot E is equal to E. Now what you have taken? AB inverse whole square is equal to E you got. AB inverse whole square is equal to E means AB inverse belongs to H. So if you take A comma B in H, you are able to say that AB inverse belongs to H. Therefore, H is a subgroup of G. Now is it okay? H is a subgroup of G. Now see. Let H be a finite non-empty subset of a group G. Prove that H is subgroup of G if and only if HH is subset. Here H is a finite non-empty subset of a group G. Now you have to prove that H is a subgroup of G if and only if H is subset of H. I think I proved this in the necessary and sufficient conditions also. Now take H is a finite non-empty subset of a group G. Now suppose H is a subgroup of G. If H is a subgroup of G means closure property satisfies. So X belongs to HH means X is equal to AB where A comma B belongs to H. Now A comma B belongs to H. H is a subgroup of G. AB belongs to H, therefore X belongs to H. Now you have taken X in HH and you are able to show that X in H. Therefore HH is the proper subset of H. Is it or not? Now see. Conversely, suppose that HH is the subset of H. Now you have to prove H is a subgroup. Let X belongs to HH, that is X is equal to AB. A comma B belongs to H. A comma B belongs to H. X is equal to AB. HH is subset of H implies AB belongs to H. Therefore, H is a subgroup of G. How can you conclude that H is a subgroup of G, AB belongs to H? Now, in necessary and sufficient conditions, you proved one condition, that is the last condition in that video. That is, if H is a finite complex, then it will be a subgroup if and only if it satisfies the closure property. If it is H is not a finite, closure property and for every element inverse should also exist. But here closure property satisfies. It is enough. So from that necessary and sufficient condition, you are saying that H is a subgroup of G. Okay? Thank you. With this I am stopping.